Okay, everybody, we're going to be talking about pH and the pH scale, and also how indicators will play into this whole acid base study. So when we look at pH scale in general, we're going to imagine that water molecules in a pure water sample will collide with each other. All right, and if you can imagine that, and when you look at the kind of reaction that this could take place, we can imagine that the um, water molecules, once they collide, so if water collides with water, I know it's a strange way of looking at this, but if water collides with water, you would then have a proton that would actually transfer from one water molecule to another, okay, and then produce H3O plus and OH minus. And if you remember what we were talking about, this is actually an acid and this is actually a base, right? And that would make this an acid on this side and this water molecule base on this side. So if you look at this from this standpoint, this happens, I don't know, maybe twice out of a billion collisions, you would get this taking place. So, and then you would simply just trade that proton back to this and then go backwards and create water molecules again. So this is continually taking place in liquid water, and there's nothing you can do about it. This is just a naturally occurring thing. All right, so now again, we look at equilibrium on this, and again, this is an equilibrium thing that happens at 25 Celsius. Again, it happens at all temperatures, but we're going to choose 25 Celsius as our focus. Okay? And so that would be the acid. So if we write a KEQ expression for this, we're going to have to be really careful because, again, these are pure liquids, and we always leave pure liquids out of expressions, right? Again, when we look at the equilibrium expression, we're always looking at products over the reactants. And in this case, the reactants we're going to think of as being 1. So you only have the OH minus, right? And you only have the H3O plus. So if we were to write this and call it the Kw for water, we would have the acid times the base. And what we find, what scientists find, is from experiment that this number is an extremely small number. Okay, an extremely small number. So basically, um, you have to think of this as being very, very, very large amount of reactants and almost no products. So you're thinking about the reactants being a huge number and then be very small products. So there's very little acid base in water. In fact, you've never tasted water and tasted anything because it doesn't taste like anything. But again, that number is very small. Now, if we know that the Kw is experimentally 1 times 10 to the minus 14th, 14th, I think we know where we're getting 14 from now, and we know that this is X and this is X, okay, because the same one of these is produced and one of these is produced, okay, then if we take the square root of this, then we realize that the amount of acid is 1 times 10 to the minus 7th molarity, moles per liter, and so is the base, because together, the 7 times this, when you do exponents, you're going to add them, you get the 14. So this is interesting, because if you take a look at these numbers, you'll see that 1 times 10 to the minus 7 is a very small number, and 1 times 10 to the minus 7 is a very small number. Okay, so again, this would be the amount of acid and the amount of base that would happen at neutral. Okay, what we find is that at 25 Celsius, as long as these two numbers multiply to 1 times 10 to the 14th, then if you know one, then you know the other. All right, so both of these have to equal 1 times 10 to the minus 14th in any neutral solution of water, or any solution of water for that matter. Okay, now again, if we talk about this in a way too, we could say that as long as if the H3O plus goes up, then the OH must decrease, so that these product of these always have to equal to the minus 14. So, for example, if this is 8, then this would have to be 6. If this was 9, this would have to be 5. If this was 3, this would have to be 11, and so on. Okay, the key is you have to lock in at that minus 14 number. All right, so for example, let's just say my acid concentration was 10 to the minus 3. Okay, well, then the equilibrium would be such that the base would have to be 1 times 10 to the minus 11, because if you take 1 times 10 to the minus 3 and multiply it by 1 to the times 10 to the minus 11th, you would end up getting this minus 14 thing. All right, so that's going to be an important part of this. All right. And again, if you look at this, it's weird because, again, if you would 1 times 10 to the minus 3, you would be you'd be 0.001, but your base would be really a lot less than that. right? So this would be an acidic solution. This would be more acidic because you'd have much more acid than base. Okay? So, I mean, it's very cumbersome to use these numbers. As you can see, it's to use these very tiny numbers with such small amounts, with a lot of zeros and small amounts of numbers. It's very cumbersome to be able to use, molarities to talk about whether a solution is acidic or basic. So simply what we're going to do is we're going to use a little mathematical thing called a log. And if we take the negative log of this number, if we take the H plus, we take a look at this number here, and we take this number there, we take this number, and we take the negative log of this number, okay? And you put that in your calculator. If you put negative log of 10 to the minus 3, basically what you're doing is you're negating this negative number and making this number a whole number. All right, so what we can do is we can take the negative log of the H plus concentration or the H3O plus concentration. It can be either one of these. Okay, it can be the H plus or the H3O plus. So if we take the negative log of that number, what we're going to end up getting is a large number 3. And that is the pH. So the pH is defined as the negative log of whatever that H plus concentration is in molarity. So as long as you can measure the molarity, you can stick it in your calculator, take the negative log, and that will produce the pH. All right. Now again, as long as this number is a 1 in front, then you don't need to use your calculator. All right. So if this number is a 1, then you can just take the number, the exponent, and that becomes the pH. Okay. To repeat, if this number is a 1, you only have to take the exponent of the acid concentration, and that becomes the pH. All right. So you can see why that, and I know we've mentioned that in class a couple times, why the pH is lower when there's more acid is because you're taking the negative of the negative exponent of the molarity. All right, that's what it is. So you can see this is 1 times 10 to the minus 3. Okay, that exponent is a lot bigger than 1 times 10 to the minus 11. All right, so you can also take the pOH, but we're not going to worry about it right now. You can take the pH or the pOH. And scientists have been known to use the pOH scale also, but technically it's really not that useful. So we usually use the pH scale. All right, so that's important things to know. All right, so how can we actually use this scale now that we have a little better understanding of what we would use it for? Okay, just a few things. Okay, so there's really 3 possibilities to this. Okay, the 3 possibilities are you could be a neutral solution where the H3O plus equals the OH. Again, this is your acid, this is your base. Okay, you can be an acidic solution where the acid is greater than the base. Okay, or you could be a basic solution where the OH is greater than the H plus. Okay, and again, sometimes we say alkaline here. So alkaline is important things to know about basic solutions. All right, another thing you want to realize is because you're dealing with exponents, that every time you go to another pH point, because it's the exponent of 10, okay, you're going to have a 10 times difference in acid when you go from one pH point to the other. All right, so if I take a look at my picture here, or I give you an example. All right, so if you go from 10 to the minus 3, which is that, okay, to 10 to the minus 2, molarity, okay, that is a 10 times jump in the amount of acid, right? Because you have more acid here, less acid here. So that would be 10 times more acid. If you make 2 jumps, then you are 100 times the acid. If you go 3 jumps, then 1,000 and so on. Okay, just also make sure that your exponents of your H plus concentration and your OH concentration must add to 14. Or if they're not, then the numbers need to multiply so that they get to 1 times 10 to the minus 14th. All right, so just a little exercise on this. Let's just say my pH is 5. What would my acid concentration be? Well, that would be 1 times 10 to the minus 5, right? You can also go backwards. Okay, and that would look like 4 zeros, right, and a 1. Okay, your base, however, would have to complement that B. Okay, and that would be 1 times 10 to the minus 9, so that you get to 14. So that would be 1, 2, 3, 4, 5, 6, 7, 8 zeros and a 1. So you can see why you're more acidic on this side, right? You'd be acidic here. Okay? And if, like I said, if we did 1 times 10 to the minus 3, that would be 3 zeros. Your pH now would be 3. You're taking the negative of the pH, right? Of the H plus concentration. And of course, what's your complement to that? That would be 1 times 10 to the minus 11, right? So that would be, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So again, I'm drawing these zeros just so you can see the relative amounts of concentration. You can see that lower pH is because you're taking the negative of the exponent, that you're going to have a larger amount of acid than base. This is your base, and this is your acid. So you're going to be much more acidic. How much more acidic here? 1,000 to 100 times, right? You can see in the decimal points. All right, and the last but not least is what they can do sometimes is to give you the base and then ask you for the acid in general as well. All right, so we can take the base and say, okay, well, how do I make 14 out of this? That would have to be 1 times 10 to the minus 10th. Okay, and again, since the pH is the acid concentration, I'm going to take that number, and that is going to be pH of 10. Okay, and again, we switched it up a little bit. Now you're going to have a much larger amount of OH, 1, 2, 3 here versus 10 zeros here. So I won't draw that out, but at least you can get a look and an idea. The next little slide here, or this little picture here, is I love this picture because not only does it show you the complementary nature of H plus and OH minus making 14. You can see each one of these setups, if you multiply them, you get 1 times 10 to the minus 14th, whether it's 13 and 1 and 2 and 12 or 3 and 11, 4 and 10, 5 and 8 and 6. Here is where you're exactly neutral, where your acid base would be neutral. Okay, and then it flips the other way. It also gives you the pHs, right? Because remember, you're taking the H plus concentration. That's how we're getting that number for in each case. You could see that that's the number. And it also gives you some everyday items that we know that we could take the pH of. So, milk being slightly acidic, pure water being right at 10, black coffee being pH 5, tomato juice, you can see your citric acids down here. Again, your strong acids and your strong base typically at the high levels. Seawater being in here at about a little over 8, okay, is interesting, right? Milk of magnesia is antacid that you would take for a bad stomach. Okay, ammonia, washing soda, by the way, is sodium carbonate. All right, that would be a carbonate ion, would be more of a basic kind of ion. So you get the idea from this. All right, so just to practice a little bit, we'll go practice a little some of doing this. It makes sense to do that. Okay, what's the pH of a solution of hydroxide ion concentration? Okay, that's interesting because in that case, hydroxide, don't forget, hydroxide is actually a base. So they're giving you the base of 1 times 10 to the minus watt. So that's 1, 2, 3, and that's 1 times 10 to the minus 4 is the base. Okay. So what is the pH of that? Well, if that's the base, then the H plus solution, the H plus must equal 1 times 10 to the minus 10. Whoops, 10. Okay, which means the pH must be 10. Okay, so just be careful on this. Sometimes they'll give you the base. Again, this is base. Okay, the pH has to do with the acid, so you have to make sure you get the acid. So that gets a little confusing. Okay, so given a solution of a hydrogen ion concentration, again, that would be acid. You may want to make sure you know that, okay, of 1 times 10 to the 8th. So if we know that, the case, then we know because this is the acid and this is the H plus, then we can just take that as the pH. The pH would be 8 in that case. All right. The OH concentration, if the H plus concentration is 1 times 10 to the minus 8th, then the OH concentration must be 1 times 10 to the whatever makes 14. So that would be 6, right? So that would be 1 times 10 to the minus 6. Again, brackets mean molarity. Litmus color is going to be, let's see, pH would be basic. Okay, so if pH is basic, all right, then litmus must be blue, according to our notes. Okay, and phenolphthalein must be pink, according to the notes, right? Our indicators. Again, you can find that stuff on table M, which we'll go through in a minute. Okay, number of times less acidic than pH 5. And again, each time you go from 5, right, to 6, to 7, to 8, you've gone 1, 2, 3. All right, so it would be 10 and 10 and 10. So whether you go this way, so because you're, if you're less acidic, because you're from pH 5 up, again, this is less acid. right? You would be 1,000 times. Sometimes they can say 1,000-fold. 1,000-fold and 1,000 times means the same thing. Okay? All right, so given a pH of 2, okay, if you're given a pH of 2, we know that's the acid already. So the H plus concentration would be 1 times 10 to the minus 2, right, because that is the exponent of the acid. Okay, OH minus would be whatever it makes complementary to 14, so that would be 10 to the minus 12. Okay, acid, basic, or neutral, well, because you have a pH 2 and it's less than 7, okay, your acid, you would be an acidic solution. Okay, litmus color would be pink in an acid, or red. You could say red. Okay, phenolphthalein would be colorless. All right, and the other time more acidic than pH 4. And again, if you're going 2, 2, 3, 2, 4, you're going 2 pH points. It would be 10 times 10. So you're looking at 100 times more acidic. All right, so that's the idea behind the pH scale. Pretty easily to know for the most part. Right? As far as indicators go, okay, indicators are simply pigments that we normally get from plants, and these pigments will change color. They will absorb hydrogen ions or release hydrogen ions, and basically change the way they reflect incoming white light. Okay, so we use them to identify acids or bases. It's typically what we do. Okay, and if you take a look at this, you'll see, again, you're not going to see this chart anywhere. This is something I put together with the chart on table M. Again, table M is your table that you'll see in the reference table that you'll get. All right, so we change color on certain pH changes only. That's the key, is the changes in pH. Okay, you're going to blend your colors through the range. I'm going to explain that in a minute. Okay, and a good example is methyl orange. So I want you to take a look at the chart for a minute, and then we'll look at the color chart. Okay, so your indicators are going to be in the first column. The name of your indicator is there. And don't get crazy with the names of the indicators. I mean, they just have some strange names to them. So methyl orange, bromothymol blue, phenolphthalein, litmus bromocresol green, okay, and thymol blue, okay. And the second one, you'll see a approximate range where you get a color change, and that's the key. It's the color change, okay. And then in this third column, what that color change is. Now, you have to understand that this is going to be a blend. All right, it's not exactly one color or the other. So red to yellow, you have to imagine that being an orange color. Okay, blue to yellow, you have to remember that. Yellow to blue is going to be green. Colors to pink or light pink. Red to blue is going to be more of a purple color. Okay, and again, yellow to blue is the same thing as the green. All right, they don't show you that on here. So if you don't know your blends and colors, that's why some of you do, some of you don't. We have to make sure that we understand. And actually, you can see bromothymol blue here. If you take a look at this area here, you'll see in between is the green color that they blend. You can see the blending of these colors. Okay, so how you would read this is, so for example, if you were looking at methyl orange, you have to imagine that if you're methyl orange, okay, if you are anywhere from pH 1 all the way to 3.1, okay, you're going to be red color. So you're going to be red that entire time. So if you're using this indicator in between 1 and 3.1, is not going to change color. So let's just say you're working in a lab and you're working at acid pHs, you would not choose methyl orange as a very good indicator because it doesn't change color in that range. It will appear red all the time. Until you begin to get to about 3.1 to 4.4, and that's where you begin to change the orange color. You begin to change that color, all right, in here. And you can see methyl orange begins to change about 3 in this area right there is where this is a useful indicator because you're beginning to change the color in that zone, okay? Now, after 4.4, all the way up to 14, this is going to be yellow. So again, a useless indicator if you're looking at neutral. And you can see that this whole area up here for methyl orange, okay, is all yellow. So why would you use it to tell you would never be able to tell the difference between a pH 8 and a pH 11 or a pH and pH 9. Okay, so these basic indicators are just simply useful where they change color. And you just have to know that, how to read it, and also know your blends. So know your blends between yellow and blue. Again, you can even see litmus. Litmus is very good because litmus happens to change really through the pH 7 range. So if you take a look at litmus, you can see anywhere from about 4.5 here. I would say it could be a little off. Litmus changes color here around the pH. Also, um, bromothermal blue being very good in the pH 7 range, in the neutral range. Phenol red's pretty good. Phenolphthalein's not bad either. I mean, it's a little bit on the high side, but again, depending on the work that you're working, you would definitely use for indicators. All right, so just to give you a little broad scope on this, you want to get an idea about the pH scale and the indicators. And again, if there's any questions, you can also check it out in class. All right, so have a great day, everybody.